So we got to help Joe make a decision. He's got 24 hours to work. He can make $11 an hour as a waiter and $8 an hour washing cars. So obviously, if he could work all 24 as a waiter, that'd be grand. But he plans to work twice as many hours at the car wash than he does waiting. Maybe because it's easier to get hours at the car wash. And he's also given this constraint that his employer at the restaurant won't give him more than 10 hours. So let's try to break these down piece by piece. We're going to do one thing here that's a little different. This is a function of x and y, a function of two variables. And this is how much money he makes. This is the function we want to maximize. He makes $11 for every x hours he works at the at waiting, and he makes $8 for every hour he works at the car wash. So if you add those together, those two things of x and y, you'll get your total amount of money that Joe has made. So let's take this next sentence. He plans to work at least twice as many hours at the car wash, which we said was y, than he works waiting. So to do that, we're going to say that the number of hours that he works at the car wash equals 2 times the number of hours that he works waiting. And you can always, if you're ever having trouble making those equations, just check yourself. If you're not sure x equals 2y or y equals 2x, try plugging in some numbers. If he works 1 hour at the car wash, according to the sentence, if he works 1 hour waiting, according to the sentence, he should be working 2 hours at the car wash, because it's supposed to be double the amount of hours at the car wash. So if you plug in that 1 hour waiting in here, that gives you 2 times 1 gives you 2, so that gives you 2 hours at the car wash, double the amount of hours that he worked waiting. So that's why we know that equation is valid. And then we also have the final constraint. His employer, the restaurant, won't give him more than 10 hours. So we have this here that x has to be less than 10. There's one last fact that we have to add in here, that Joe can only have, he's only working for 24 hours. So X represents the amount of hours he worked waiting. Y represents the amount of hours that he works at the car wash. So if you do X plus Y, that has to be less than 24. So to find a solution to these types of problems, usually the way they're set up, especially in an algebra course, is that if you graph all of these, you can find vertices for where they all cross. And if you can find out exactly where they all cross, then you can find your optimal solution by plugging them in. So let's start by graphing this. This is y equals mx plus b, except b is 0. Y in this case is 2. The slope is 2. So we're going to rise 2 and run to the right 1, but we start at the origin at 0. So I'm going to go by 5s because I was taking a look at all the numbers I have here. I've got 24 going on. I've got 10. I've got some pretty big numbers. So instead of going by 1, 2, 3, 4, 5, I've just made my x and y units consistent. I went by 5. So let's go back to this one. Y-intercept of 0, slope of 2 means you rise 2, run to the right 1. Or in other words, you rise 10, run to the right 5. Because 10 over 5 is the same thing as 2 over 1. So we've got a dot right here. Then you can go up another 10, to the right another 5, got another dot right there. So we've got a straight across line going this way. Okay, so that one's taken care of. So to graph this next one, x is less than 10. X equals 10 is right here in the x-axis. And if you're not sure if that's a horizontal or vertical line, if it's a horizontal line, it'd just be right on the y-axis. It's a vertical line going straight up and down. And actually, I think they said they could have exactly 10, so that should be like that. Could have 10 hours at the waiting place. So that's why I drew a solid bar, because it could be exactly 10 hours. So that one's graphed now, and then for this final one, x plus y is less than or equal to 24. You could do this by by intercepts. I call it the cover-up method. Cover up the y variable as if you're plugging in a 0 into it, and you get x is 24. So I'm going to put a dot somewhere close to 24 right there. And then do the same with the x variable. Cover up the x variable. Cover up the x variable. And pretending the y is still there. Y equals 24 for that graph. So that means we got a y-intercept over here. So that's enough to graph. We can just draw a line going straight through those. Oh, gosh. Let's try that again. There we go. Line going straight through. Okay, so we got to meet all these conditions. And then we also have to keep in mind that it says less than. So we should draw arrows to remind us. Oops. Yeah, that it has to be less than this line. Okay, so I think we got everything. So keeping in mind that this last equation that we just drew, x plus y is less than or equal to 24, we're going to want to try to maximize our f of x comma y thing. We want to find out the biggest number that's going to work for this. And the way you do it with these linear optimization problems is you find out the vertices for where the lines cross. We're not going to worry about the triangle because there's no solution inside the triangle. This is where this would be greater than 24 if you were to plug in numbers here. That would violate this yellow line that we drew, the line for the total amount of hours you can work. So it's got to be something over here. So that means it's either this vertex is the maximum or this vertex is the maximum. We know this is going to be the maximum. Working 0 hours isn't going to get us anything. And working 10 hours at the restaurant leaves us out the 14 other hours we could be working at the car wash. So we're going to forget these. We're going to try to find out where these two cross exactly. And the way you do that, and the way you do this for any type of equation in math, is if you need to know exactly where they cross, like we need to know where this red line and this gold line cross, you take them and you set them equal to each other. Or you plug one into the other. In this case, I got y is 2x. So down here in this equation, I'm going to replace that y with 2x. And then I've got something I can solve. So using the substitution method, that helps you find out exactly where two things cross. We get 3x is 24, or in other words, x equals 8. Divide both sides by 3. So the x coordinate for where those cross is at x equals 8. And to find out the y coordinate, you can actually take this x equals 8 and plug it into either of the two equations. Plugging it down in here or plugging it up in here should get you the same solution. If you plug in 8 right in here, that's easiest. 8 times 2 gives us 16. So get y equals 16. 8 comma 16, we just found out that's where the red and where the gold lines cross. So to find out where the gold and the blue lines cross, that's what we're going to do the same type of thing again. We're going to take what was our blue line, which was this guy right here, and we're going to plug that into the gold line. So if you just plug in x equals 10 into this, into the gold line that we had down here, then you've got something you can solve. And I'm putting an equal sign in here because we want to find out where they exactly cross. We don't need inequalities anymore. We don't need less than or greater than. So I want to find out where the blue line crosses with the gold line. So that means I'm going to plug in 10 in for x. Then I can just finish solving that equation for y. But it's pretty clear that y has to be 14. So we got x was 10, y was 14. That's where these two cross. Okay, so we found out where those cross. That's a small point, but 8 comma 16, 10 comma 14, those are going to be the optimal solutions. We said we're going to rule out these ones because working 0 hours certainly won't give us the most money, and just working 10 hours at one job, nothing at the other one, that's not going to help us. So we're going to plug both those coordinates into this function because this is the thing we wanted to maximize. So let's start with my green point first. Oops. So it means I'm going to plug in an 8 in for x and a 16 in for y. So when you simplify, 11 times 8 makes 88. 8 times 16 makes 128. So add those together, get 216. So that's what we got for the green point. Let's go through the same process and plug in the blue point. So if you plug in 10 comma 14, you get 110 plus... I don't know what that is. Plus 112. So if you add those up, you get 222. Okay, so let's compare. We got 222 for the blue point, 216 for the green point. So it looks like 222 was our optimal solution. If you do 10 hours at x, which we said was waiting, the maximum number of hours, and then if you do 14 hours at the car wash, you've maximized your solution. So this is going to be our answer. 10 hours waiting, 14 hours at the car wash. It meets all those constraints, and it maximizes the amount of money he's going to make.